Hey everyone, welcome to our Introduction to ML seminar. I'm Kevin Xu, a sophomore at the college studying computer science and physics.
I'm Zed. I'm a sophomore at Harvard College studying computer science and maths.
And we're so excited that you could join us here today. We know that we're in the middle of final test week, and so everybody's probably a little stressed. So hopefully we can give a very interesting and hopefully fun presentation about what to look forward to as you start implementing your final project. So just some logistics first, we will have some set points where we'll take a few questions from the audience. So feel free to type them into chat as you think of them, and somebody will probably read them to us when we pause for questions. But yeah, other than that, let's just get straight into it. All right. So of course, our seminar is about machine learning, or ML. And so the first question, which is not so obvious, is what is machine learning? And so I'm sure a lot of you have heard about the developments that have been in this field, a lot about neural networking and perhaps reinforcement learning. And a popular topic, of course, is the game development theory, where some computers have solved games through these complicated machine learning algorithms and neural networks. And so we just want to give a quick overview of like what exactly falls under machine learning. And this is actually a very broad category that includes a lot of different sub-ideas and sub-fields. And so there are three main ones. There's unsupervised learning, supervised learning, and reinforcement learning. And a lot of the neural networks that you think about when you think about machine learning and reinforcement learning fall under one of these categories. But at the end of the day, ML is about taking a lot of data and having the computer or an algorithm or a program process the important parts of that data. Recognize the patterns in the data and attempt to use that data to generalize to a bigger data set that you might be given. So Zad now is going to present a little bit more about what exactly these subfields in ML are.
So the first thing you want to know is about supervised learning. So what is supervised learning, right? So given some labeled data, say for example, we have a data set of cat and dog's picture. So how can a machine learn to predict the labels that generalize to unseen data? So what we do is we put like a data set of cats and dogs picture and then put it into a machine learning model. And like the machine learning model kind of like learn itself on how to differentiate between cats and dogs. And then we have some testing data set. We maybe have cats and dogs, or maybe other images. And the machine would kind of like label, oh, this is a cat, or this is a dog, or this is not a cat or a dog. So this is kind of like a supervised learning, machine learning, whereby we actually label the data so the machine can learn from it. So the next big idea in machine learning is also unsupervised learning, where the machine actually recognizes the pattern itself from the data. So like we don't label anything. We don't label it's a dog or a cat. We just show all the images to the machine learning. And the machine will be like, oh, this feature kind of like assemble a cat, so this is a cat. And this feature kind of assemble a dog, so it's a dog. So that's kind of like a difference between unsupervised learning and supervised learning. And most of the time, unsupervised learning include like clustering, for example, in like a very high dimensional ICU data, like who is most likely to get re-admitted and what is the features that those people are going to be admitted or not. So that's kind of like a difference between supervised and unsupervised learning. And next, Kelvin is going to talk more about what is neural network and why it's fall under unsupervised learning.
Yeah, so as Dad mentioned, a lot of the time you're dealing with data sets that are like hugely multidimensional. And all that means is there's a lot of different categories that you can consider, such as an election, like the population, the demographics, how likely the other candidates are, et cetera, and you just have all of these categories of data that you need to somehow compile together and get some reasonable kind of prediction as a result. And this is where neural networking shines. And if you continue in researching this field and perhaps continue with this kind of topic, you're probably going to see this kind of picture a lot. And at first, this looks very incomprehensible. It's just a giant graph with a bunch of nodes and lines. But this is actually just a very brief picture of what neural networking is. On the left, you can consider these as input nodes, and on the right, you have output nodes, and in the middle you have hidden nodes. But this doesn't really tell you anything about what this does. And so you can think about this giant network of graphs, or however you might imagine it, as just a black box function. And this black box function takes in your input data, so the different categories, your multi-dimensional input data, and then it spits out the output data, that it should be good enough for prediction. So in the most simplified case, let's just talk about a game, such as tic-tac-toe. And so your input data just might be the state that you're currently in. So what squares are filled, whose turn is it, et cetera, et cetera. And your output data might just be one single number, that's a heuristic between 0 and 1. And all this number tells you is how good your current board position is. So obviously, if you can make 3 in a row in your next turn, your heuristic should be very good. It should be 1. And if you're going to lose in the next turn, it should be 0. So obviously, not every state falls under this case. So there's a continuous range of numbers between 0 and 1 that your black box function should be able to retrieve or accurately predict from this input data. And this is the job of like everything in the middle, right? How do these variables relate? What function or like what functions you should apply to these variables in the middle of processing, et cetera, et cetera. And so the overall goal of neural networking is to design this middle function, right? How do you get the computer to find these patterns and to create this black box function in a reasonable manner? And this is something that's really hard for humans to do because there's so much data. And so we give it to the machine instead.
So a general outline in a machine learning project or machine learning research, for example, we start with like a data collection. So there are a lot of different ways where we can collect data. Some significant ways like finding sources of data is like scraping it from websites, API call, or readily available data sets such as Kaggle or like in UCI ML repository. But do take a note that scraping raw data, for example, from like API call or even websites may take a long time to clean up the data, especially when there's a lot of empty rows and stuff. So the next step we do is normally data exploration. And initial data exploration is normally very powerful and it gives very insight on what features to take in, what features to drop, whether your data is biased, and understanding the dimension of the data is actually very important. So the third one is, of course, choosing an ML model, like choose a simple model to start with. Say, for example, what is the type of problem you want to solve, right? We'll go too deep in that in an example later, but like some problem I consider is either a regression or classification problem, or whether to actually use a supervised or unsupervised machine learning model. There are some models that you can choose from. And the fourth one, after you choose a model and code it out with all the libraries, it's like you get the result. You want to test it out. Like, what is the accuracy score of your model? What is the precision? What is the recall score of your model? And how can we improve the model? Like by fine-tuning the parameters or even using other more sophisticated models. Say, for example, start with logistic regression, maybe you can move on to neural network. So I think we can start with a bit of questions. If you guys have any or not, we can move on to examples that we have.
Okay, there's one question from Pratik. Is there any difference between data science and machine learning?
So, yeah, do you want to take this on?
Yeah, sure. I think data science is more, I think machine learning is under data science. You can correct me when I'm wrong. I think like data scientists somehow also uses machine learning model to help them to analyze the data. So basically what it means for data science is that like we try to understand the pattern or like what useful information can a huge amount of data tell us, right? So I feel like machine learning model can be a very good stepping stone into data science. And also there are like statistics as well, like pure statistics, such as like chi-square test, which is not really machine learning, but also like part of data science.
Right, just echoing what Dad said, ML is a technique or you can almost think of it as like a methodology to approach the study of how you can extrapolate data. And so there's a lot that falls under this, that falls under machine learning, but there are also a lot of things that you can do that are not machine learning, right? And so I hope that answers your question.
Okay, no other questions. You can continue. Yep.
And that will end it quick.
So you guys can go to this link if you want to make a copy of the notebook yourself and follow up when we actually present it. You can go to this tinyurl.com and our notebook/1. We will jump straight to the notebook and we can show you. So there are a few contents if you want this table of contents, and I'll close it so we can have a better view of it. So let's get started. We talked a lot about how we can start with machine learning research. So in this particular notebook, we will try to use Iris dataset, one of the most famous dataset about machine learning. So in a supervised learning, we will try to use two different model, which is K nearest neighbor and logistic regression. And the second part, we will jump into reinforcement learning with a different example. So as we talked about last time, the ML development process include like data collection, train, test, split, identify correct ML problems and ML model to use, evaluate the performance of the algorithm, and try different like models and retrain to retest. So let's get started. The first thing you want to do is, of course, import the necessary libraries like pandas, numpy, plotting library, train test library. So we'll get straight and run this. So to run a cell in Jupyter Notebook or like Google Colab, you just press Shift Enter. And so the next thing you want to do is to import the data set that you talk about, which is the Iris data set. So this data frame.head is to print out like, oh, how the, like, it's to give you an idea on how the data frame actually look like. So we can see that if we run this, there's support length, and then paddle length and paddle width, and there's target. Target is the three different things that we have, which is, I think, different kind of iris. And the next thing you want to do is try to explore like what is the shape of the data frame, for example, right? Now we know that there's 150 rows and 5 different columns. We can see there's 5 different columns and there's 150 rows. So let's talk about like the first thing we want to do is to actually explore and analyze the data. That's because like it's important to do initial data exploration because it might be biased, it might be noisy, and it shows the relationship between different features and target and better train our ML. So I put some links here that you can use next time, but like we will start by plotting a pie chart between the different targets. Like there's Sentosa, Virginisa, and VC color. That's a different type of iris. I can see that like each of them kind of like 33% represented very equally and balanced in the label data set. And this is to plot like the number of different labels versus this is the number of like count, and then this is the width. So you can see that like most of the pad, like say for example, support width, you can see it fall under like 3.0 to 3.5, and it's kind of like evenly or normal distributed. And this is more like a graph to see different kind of length and width vary according to species. And it might take some time. And I think this is very useful. And this is basically a pairwise plotting between how the features and the target are influenced. It takes some time to plot, but it'll be cool. So say, for example, look at this, right? We can see that like paddle length has a very huge influence on the target. You can see that like for target 0, they have really, really significant smaller paddle length as opposed to like target 2, which actually have a very clear, distinct features. And moving forward to actually, you know, like sometimes when you look at graph, it's not intuitive. So a very, very good way to plot the intuition, like to calculate, to see the relationship between different features is to plot a heat map. You can see that when we plot a heat map, we can see the higher correlation between paddle length and target. This is what we want to label, right? Paddle length and target, and paddle width and target. So like we pass into the machine learning model where we can actually drop, which means delete the column of support width and length because it doesn't really correlate to the target that we actually care about. So the next thing I want to do is to train test split. The importance of train test split can be learned more about here, but we will just move on. So basically, when we have a data set, we can't just put everything into training sample. We need to split it into maybe 70-30 split, which is 70% training and then 30% testing, or 80-20, 80% testing and 80% training and 20% testing. Depending on the size of your data set, some people go with 70-30. If you have a huge data set, you can actually do 80-20 split. So in here, because we don't have a huge data set, we only have like 1,500 rows. So I decided to go with 70-30 split, which we can see that the test size is actually 0.3. And we have, after splitting, we get like 105 rows in the training data set and 45 rows in the testing data set. And we can also check whether we actually train it correctly. And this is a very important step whereby we actually split So now we have 5 different columns, right? We have support length, support width, paddle length, and paddle width, and we have target, and this is what we want to test it out. So we need to split the training data set into both X and Y, where we have these are called features, and then this is the target that we want, and these are all features that in the testing data set, and this is the target. So we split that. All of this can be found in, this is actually under pandas. If this notation seems really, really weird to you, it is very well documented in the panda data frame. And this is still head, and we see how it looks like in this. So after I split it, you can see that like train X now has like 4 different features that we want to train it on, like the head, which is, this is the attribute of it, which correspond to the ID features. So the next thing we want to do is identify correct problem and ML model. So in this problem, it's more like a classification problem. So for example, if we are provided with several inputs and variables, a classification model will actually try to predict like the class of the kind of like data. So say for example, here is a classification problem is because we are given the features support length, support width, paddle length, and paddle width, and we want to find like what target, which is what kind of iris species it is. So that's a classification problem. As opposed to a regression problem where we are given certain features, we want to find like the paddle length or paddle width, that's a regression model. You can read more about here. I'll not go through for time's sake. And before we move on to test out about model, I want to talk about evaluation metrics so we can keep running and see it. So there are a few, before we dive into evaluation metrics, we need to understand what is a true positive, true negative, and false positive and false negative. So true positive is when outcome correctly predict the positive class. Say for example, you have a 1 and then the model actually correctly predict the 1 class. And similarly, a true negative is an outcome where the model actually correctly predict the negative class. Let me give you an example. So basically say we have a cat data set and a not cat data set. So a true positive is whereby a model correctly predict that it is a cat. A true negative is when the model actually correctly predict that it is not a cat. So that's the difference between true positive and true negative. A false positive is an outcome where the model incorrectly predicts the positive class. Say for example, I have a picture of a cat, but then my model predict it as not a cat video. That's a false positive. And a false negative is an outcome where the model incorrectly predict the negative class. That's when like I fit in a non-cat picture, but the model say this is a cat. So that's a false negative. So in terms of like a different kind of metrics that we use in judging the performance of a ML metrics, we have accuracy, recall, precision, and we also have other called the ROC curve, which is receiver operating characteristic curve, and AUC, which most often used as opposed to ROC, which is area under the curve. So accuracy by its meaning is the fraction of prediction that got right. Say, let's take the example of the cat and non-cat data set, right? So the fraction of out of like the 150 predictions, for example, like if my model predict 96% of the cat picture correctly, that's an accuracy. And also we have recall, which is what proportion of actual positive are defined correctly. So mathematically it's defined as like true positive over true positive plus false negative. And precision is true positive over true positive plus false positive, sorry. So it's like what proportion of positive identification were actually correct. I know that might be a bit like overwhelming to like hear a lot of like true positive, true negative. It's like, oh my God, this is so much. I included like a lot of different resources that you can actually go and read it. I think there are pretty good resources whereby you can learn more and get accustomed to all of this term. And so let's first dive into the first machine learning, the supervised model that we're going to talk about, which is K nearest neighbor. So the K in K nearest neighbor is the nearest neighbor we wish to take the word from. Let's do an example, right? So this is a dot that I want to label, like whether it's a blue dot or a red dot. And the radius of 3, which is this like what's it called? A solid line circle. You can see that like we have 2 red triangles, but 1 blue square. So in this case, this dot will be classified by the K and N label as the red triangle. And what about if it's larger, right? So what about K value of 5? So it will be the dotted line circle. So you can see that in this dotted line circle, we can see that if we classify this green dot, we have three blue square, but we have 2 red triangles. So this blue dot based on this dotted line circle will be classified as a blue square. So we can see that actually choosing a K value in the KNN algorithm is very important. And that's where all the time consuming part come in, because you want to choose a correct model that doesn't overfit or underfit the algorithm. So some of the way that you can do it is plot a graph of accuracy versus K value, or graph of error rate versus K value. But most of the time we just test with a random one and then we move on from there. And there's also different metric system that we can use. If you learn maths, we also learn about the Euclidean distance, whereby it's like draw a triangle and then we have the Euclidean distance, or we have the Manhattan distance, whereby it's like the longest distance from a point to a point. So the KNN resources that I found really, really helpful in explaining will be here as well. So without further ado, let's get started with like model testing. So I use an sklearn model I pass in my K neighbor, which is 3, and I pass in a KNN classifier and I train it. And after that, this is the prediction. After I train it, I just use the model to predict my testing data set to see how accurate it is on the data set itself. So after I run it, you can see that the accuracy score was around 93%. That means that like of all the of all of the prediction that all the ML model made, 93% of them are correctly. And what about the precision score? We got like a 0.9476, around 95%. That means that out of the total positive observation, 95% of the prediction is actually correct. That's pretty high. And the recall of the KNN is around 93%. I'm so sorry. I will change this later. But maybe let's test around with a different kind of neighbor score, right? Let's say about 10, which is basically overfitting. So you can see that like it actually affects I think just now we have like 93% accuracy, but now we can see that like if we fit it with an amount of like 10 neighbors, which is like increasing the radius of the circle, you can see that the both the precision and accuracy and recall score actually increased from like around 93% to 95%. So that's why like constantly testing and evaluating the model is actually very important. So let's move on to another one, which is logistic regression. Logistic regression mainly based on this graph called the MLE, maximum likelihood estimation. Giving an example will be, say, for example, I was given a bunch of data and I was trying to predict whether someone is COVID positive or COVID negative. So what we will do is we'll plot a graph like this, a sigmoid curve, and then say the data was here, right? And I'll be like, oh, because this data was around like more than 90, like more than half of this curve, I will classify it as 1. What if it's like here, we'll classify it as like COVID negative. So that's how this model generally works. Is that like, depending on where the data points are, we classify whether it's positive or negative based on where it is. So in this case, we also try to run a logistic regression model on the iris data set itself. And I also include like a few resources where you can understand logistic regression more. So if we run the logistic regression, sorry. I think it's actually not. So if you run the logistic regression, you can see that the accuracy score is actually less than the one that we had before. We have like 95% of accuracy with KNN model, but we only have around 93%, sorry, 93% with like logistic regression. And that's how we actually, so alternatively, you can use other approach or ML model that we suggested here. Sorry, you keep jumping, which is decision tree, support vector machine, or neural network. I remember when you run it across support vector machine, it has really good like accuracy and prediction. While neural network is also a pretty good way to try to classify it. So that's all from me. You can run on to.
Yeah. So great. Dr. Zad's a wonderful job of highlighting how you can use a regression, or you can use ML to take a data set and attempt to predict future elements that may be part of this data set, right? And so this is one of the core pieces of ML. And don't be worried if you couldn't follow all of that, or you don't really understand how the syntax for the code works. It's learning new libraries, and machine learning is very heavily dependent on previously written libraries. It's a lot of work to develop your own algorithm for the machine learning to take place. And so a lot of the time it's the case of seeing how your data looks and then trying to choose the best model, which is a sequence of algorithms that make this black box function, as we talked about earlier, to actually get accurate predictions. So yeah, feel free to ask questions about, or like post questions about this. But I will be going on to kind of the flip side of machine learning. Instead of using previous data to predict elements of the same data set, we're going to start talking about how can we get the machine to calculate, or like we're going to start talking about games and reinforcement learning. And so one of the most popular uses for reinforcement learning is, of course, trying to solve games, right? So you have a game and you want to build a artificial intelligence or an AI that best wins your game, or that always plays the best move possible. And this is actually like loaded with theory about like how data sets work, how like the game itself works, and there's a lot of math and logic behind it. But at the end of the day, the idea is, given what you know about the game, can you get your computer to train on the game such that it always has a pretty good idea of what the next best move is? And so I built just a really silly game here. We don't have to worry too much about the structure of the game itself, but in general, essentially, when you start the game, you're presented with two doors. You choose one of the doors, and then you're presented with another two doors. And you choose one of the doors again, and behind that door, there's a randomly generated value between 0 and a certain number that corresponds to the door. So if you think about like this kind of tree-like structure, you have 2 and then 2 more, so there's 4 total doors at the end, and each one of them has a number assigned to them, perhaps like 9, or in this case, I think 3, 9, 1, and 20. All right, so obviously the door that is associated with 20 is going to, on average, give you better points or reward or whatever this point system works out as, right, than the door that has a 1 associated with it. And so the question is, can you get the computer to realize which door is the best simply by playing the game a bunch of times, right? And this is the concept of reinforcement learning. You just play it a bunch of times, and for things that turn out well, as in you've got a lot of points, and well, yeah, you've got a lot of points, then the computer should be more likely to choose that option in the future. And for doors that you didn't get a lot of points, you should be less likely to choose that door in the future. So we don't have to worry too much about the overall structure of this code, but right now I have it set up such that the computer just simply plays random moves every time. So it goes through one of the 2 initial doors with equal probability, and then it chooses one of the next 2 doors with equal probability. So you expect that the expected value is going to be pretty low, because these are in general pretty yeah, so it won't be the highest that it could possibly be, right? So if we run this code, we get an expected value of about 4.125. So on average, the computer is scoring 4 points, right? And so this is definitely not the best we can do, right? This is a totally random, the computer is playing totally randomly, like this is completely stupid for the computer to do. And so we want to attempt to get it to figure out which doors are better. And this actually doesn't have to, to implement reinforcement learning, a lot of the time, neural networking and other aspects of machine learning are incorporated with reinforcement learning. So like you take in the data and you pass it through another regression or prediction, and like that also helps you find out like which move is best. But in this case, because the game is so simple, you can simply just hard code the training in. And so if we take a look here, and this will be a little brief. So if you want to ask about the logic, go ahead in the chat, but I'll try not to waste too much time trying to explain what every line of code does. So for every move you take, you consider the state that the move resides in. So the current state of the board, so which doors you have in front of you and which possible doors you can go through, right? So if you're starting at the beginning, you have the first two doors, right? So your state is just at the beginning and you have two possible choices. And so if you label every state in the system with a heuristic value, that basically tells you the goodness of that state. Like how desirable is it to be in that state if the goal is to accumulate points? Then what you can do is have the computer simply go through the states that have the highest goodness value, right? So how do we actually calculate this goodness value? Well, we just play the game a bunch of times. So for every time you play the game, you're keeping an internal track, or the computer is keeping an internal track of what the current state heuristic value is, and then it makes a move based on what it thinks is the best move in this case. So here, once we make the move, we then find out what the next state is and how good the next state is as a result of the move. So using this accumulation, we can kind of backtrack and see how good was the current state that we were in before we made the move, and how good of a move did we make. And so, of course, by incrementing these, right, you increase the probability to make good moves, and you decrease relatively the probability to make bad moves. And so, if we throw this training in, that calculates the heuristic model, and we recompile, we get an expected value of about 10, which is about twice as big as we had previously. So the computer has gotten way better at this game. And if you actually take a look into the data structure, which I won't at the moment because it looks really complicated, and well, it's just a big dictionary and I don't think it will help you understand what is going on here. If you actually take a look, you'll see that the end result of the training, so the training, we played the game 10,000 times and we evaluated the goodness of every move for those 10,000 games. And you'll find that after this training, the probability of getting, of choosing the door that leads to this 20 door, oh, sorry, I went a little hard. So that leads to this 20 door at the end is almost 1. It's like 0.9997 or something like that. And so the computer has basically figured out, without us telling the computer anything except for the game, right, the game state and what the results are, how to beat this game. And so this is the goal of reinforcement learning. And I think this is a very interesting thing that has, there's a lot of application in chess and Go. And this is the basic core idea of how people have solved these games. You want to make good moves is what it boils down to, which sounds very simple, but in execution can be more complicated than it.
Kevin and Zed, can we take a couple of questions now? Oh,
yeah,
perfect.
That's what we were answering right now.
There we go. All right. There have been several since the last little break there. Okay, from Angela, was person of interest a realistic example of machine learning?
Person of interest?
I'm sorry, can you repeat the question?
That's the question. It was probably about the earlier, maybe Angela, you can write back in the chat. I'm going to just keep going on and continue answering. But if you want to clarify that in the chat. From Maria, do you ever feel like machine learning sometimes have very serious sequences, like in elections, for example?
Yes, we do feel like in terms of machine learning, the impact of machine learning model, especially, like, I mean, it can be both bad and good. That's why, like, at the last slide of our slide, we also talk about how machine learning actually generates deepfake or, like, you know, privacy intrusion, the alignment problem. So we actually include some machine learning ethics that we hope to actually share with you as well. But generally, in terms of machine learning in election, I do think that that's true, because a lot of the time, advertisement model in like Facebook or Google, they use a lot of machine learning model to predict the kind of person that you are, and like recommended system is actually a part of machine learning. It's a very huge research topic in machine learning. And so if you want to know more, it will be recommender system at Google or Facebook advertisement.
Okay, and then we have another question about cybersecurity. So is that, I think we can leave that for later. I think you have some slides on that. Is that correct, Sad? Yeah, okay. So
Yeah, we do.
all right, so let me just, this is from James. How does a computer machine recognize objects by itself in unsupervised learning?
It depends. So for example, if you say like a data point, for example, like currently I'm doing research on like the ICU data, say we have a lot of features, and then so what we do is like we pass in the features, and then it will be represented in like let me give you a simple example. Say for example, we have X and Y feature, and we recommend it on we just plot, like we just put the points in, and then how the machine learning knows is that they try to cluster the point. One of the very good way to actually know, like in unsupervised learning, is clustering. So basically, like say for example, I took a point, right? Like what is the neighbor of the point and how it actually relates, how strong it actually relates. So maybe like for example, like the points are like very separated, or like the points is like a block, or like the points are not related at all. So basically, one of the very good way of unsupervised learning is also clustering. That's like for discrete data set. If you say for image data set, for example, most of the time we use something called the convolutional neural network, which is CNN, which is basically pass through a lot of filter. I think in CS50, we also have this piece that we talk about ages detection. I think it's under the, it's one of the P set. And there's an edge detection whereby like we draw out the edge itself. And that's also a part of the CNN whereby we try to pass through different filter and network, and then we draw out the edge to recognize what is the image itself. So if you are if you're interested in knowing about how machine learning actually understand images, I would recommend CNN. If you're like normal unsupervised learning, there are a few where we can say here is like clustering autoencoder, which is a part of neural network.
Okay, why don't we take two more and then we'll continue again. So Amir asks, which step is preferred? First, data analysis or machine learning?
I would,
So this is like very context dependent at times, but in general, you don't want to take some data set that you just gathered and immediately throw it into machine learning. Because when you take data in the real world, as opposed to generate data, there's a lot of noise. There's a lot of inconsistencies. There's a lot of things that can go wrong just when you take normal data. And so if you just throw something like something random into an ML program, it will not necessarily get you the results you want. And most of the time it won't, because there's so much noise in the data that it's really difficult to identify the patterns. And so generally, when you're designing this this type of sequence of steps, you want to at least like screen your data before you throw it into any type of program. That way you can catch early on if things are going to go wrong, right? And like in the worst case, you just might have to retake the entire data set because it's not valuable, right? And so it's kind of like a screening process, at least the initial data analysis, before you can actually try and be productive with that data set.
Adding it on, I feel like it's very important to do data analysis first. It's because, say, for example, you get a data of like COVID positive and COVID negative patient. And it actually is very dangerous. So for example, if your data set is very biased toward COVID negative person, and you just pass it to a logistic regression model, and the model will be like, oh, since 98% of the people are actually COVID negative, right? Then I can just predict like, oh, like out of the test example I gave, I will just predict everybody as negative. So I still get a 98% accuracy, which is actually very, very dangerous. And it's one of the way why you want to know how many like labels that we have before we actually pass into the machine learning model, because this kind of biases can happen. Machine can be just like, oh, because 98% of people are actually like negative, so I can just predict everyone as negative and I get a 98% accuracy, right? So it's very, very important to do the data analysis before you actually train the data, especially on like this kind of highly biased data itself.
Okay, and the last question from Victor, do all machine learning models use neural networks?
No.
Yeah, no. So neural networking or convolutional neural networking, these two things, or same thing, but specialized, are a specific subset of the machine learning that you can do. And so I think you probably asked this before I showed the reinforcement learning example, but you don't have to use neural networks at all when you're trying to get the machine to learn. Neural networks are very powerful because you're able to take a lot of data and have the computer generate the relationships between the data, but it's not always necessary to use a neural network when you're trying to learn from a data set or have the computer learn from a data set. As you saw in like reinforcement learning, right? You can simply have the computer attempt to make its own conclusions based on what state or like what type of data you give it and what it wants to achieve. Great. So yeah, we'll take some more questions at the end. So yeah, feel free to continue posting them in the chat. But for now, since we've probably hit you with a lot in things we can do and things we can't do and possible things, we want to give some tips on what is reasonable to consider if you're actually attempting to implement this in a CS50 Final project. And so Zad has made this great graph here that goes kind of in difficulty level from the left to right. And so at the very left, you have supervised learning and unsupervised learning, which is requires some effort, but not like huge amounts of dedication, although this is always context dependent as well. And then reinforcement learning will probably take more time, simply because you not only have to provide the data, but you often have to build an infrastructure that can interpret the data. So in the case of the game, right, you have to build something that actually, you have to actually build the game into Python, where the game has to take in an input state somehow, and it has to return to you the new state and the results. And so there's all this extra infrastructure that you need before you can actually run any ML. And sometimes this takes longer than running the actual ML. I actually spent longer trying to get this infrastructure to work out than actually like implementing the reinforcement learning. So this is like very something to be cautious of if you're interested in doing something like solving a game. But of course, it is certainly doable if you are willing to put in the extra time to do it. And then with like convolutional neural networks and deep learning and some of the higher stuff, we caution against it unless you are very familiar with this kind of construct, and it requires quite a bit of in-depth knowledge. So you don't really have to worry about that. And so quickly, I just want to mention how you can actually implement these things. So we used Google Colab, which runs Jupyter Notebook, which is a Python interpreter that goes line by line. So the nice thing about Google Colab is that, well, there's two nice things about Google Colab. One is that it interprets line by line. So you can change a line without having to rerun the script from the top down, which is great if your things take forever to run, as is often the case in machine learning. And the other nice thing about Google Colab is that it's cloud computed. So there's a GPU on the server end that does all this and then returns it to you over the web. And so you won't try and break your machine trying to process like 10,000 images. But on the other hand, if you feel comfortable running it on your device, it's certainly doable. I ran the reinforcement learning code just fine on just a terminal on my device, and those are the kind of things that don't really take too much processing. So yeah, just keep that in mind when you are thinking about how to actually implement this.
So next, I will talk about like the useful Python library that we like normally use for machine learning. The first one we will go into like is data. How do we get data, right? So in terms of mining data from online, we can go for Beautiful Soup, which is a kind of like a scrap libraries that someone wrote about. It's all linked, so you guys can press in. The slides are available on CS50 website. And also Scrappy, which is one of the very good scrapping library. And in terms of like built-in data sources that are very well documented, I would recommend Kaggle. It's a Google platform with a lot of machine learning data. And UCI, University of California, Irvine machine learning repo, also a lot of like data sets available. Or like you can also scrap from website or API call with like Beautiful Soup or Scrappy, or even your own API call. And for data pre-processing, I'm a very huge fan of pandas. So I'll highly recommend using pandas, like changing your CSV to pandas and just work from there. It's actually much more efficient and useful. And there's also like NumPy and SciPy, which is also like things that we normally use in terms of calculating mean, median, and a lot of very useful functions to analyze the data or pre-process the data. So the next thing is Python library, which is like visualization. The most simple basic visualization library that is available online is Matplotlib, very useful, super well documented, a lot of example online that you can use. Seaborn is a better kind of like visualization where you can choose your own color map or like better kind of visualization. The best visualization that I can actually think of, maybe not the best, but like Plotly is a very highly visual, very engaging, highly visual, very nice visualization libraries that Python has. So in terms of ML models, there are a lot of built-in libraries. You can also build your own ML model from scratch from Python, which actually increase your understanding on the model itself. But if you want to save time, if you just want to use the model itself, there are a lot of built-in libraries. Say, for example, sklearn is a very good library for beginners. There are like various classification, regression, and clustering algorithms that we can just use. And there are also TensorFlow, I think a Google kind of like a Google deep neural network Python library. It goes for various tasks. It's on training and inference, mostly on deep neural network. And they have pretty good documentation online and on YouTube and really good tutorial. We also have PyTorch, where it also runs on neural network, computer vision, and NLP. And we have Keras. I think Keras is by Facebook. And it's primarily for developing and evaluating deep learning models as well. Those are really, really useful library that and are really well documented. There are a lot of tutorials online that we actually recommend. And it's also linked, so you guys can actually have a look too. In terms of ML resources and support from CS50 and beyond, we actually recommend you to go on ad if you have any like bugs that you don't know how to fix. The CS50 team are really, really happy to help you on ad. And we also have CS50 Intro to AI classes online too, so you guys can have a look at it. There are also a lot of Python libraries documentations online where I highly recommend you to look over the examples before you actually start coding. Kaggle is a place whereby all the data scientists go. They are like data sets. There are also like example codes that you can try it out, and also competition that you can join. Very good place to learn about data science and more about machine learning. And there are a few blogs that we found very useful as Towards Data Science blog is by Medium, and Machine Learning Mastery blog is a free blog that's really, really helpful. Of course, we have our favorite Stack Overflow and GitHub, really, really good ML resources and support there as well. So let's talk about the ML ethics that we actually see, like a lot of questions about like what is the bad, like machine learning can do so much good stuff, right? Like it is used in healthcare, education, anywhere that you can think of, but at the same time, it's had its own like danger itself. So for example, one of the things that we see the most is deepfake. And I think Malan actually did a deepfake example video in last year's CS50, which is actually very exciting. I highly recommend you guys to watch. I actually link it here so you guys can watch it later. And another thing about machine learning is actually it's a black box. So it's like interpretability in machine learning is a huge topic that a lot of machine learning practitioners are actually talking about. So one of them is Professor Finale, also a professor at Harvard. She actually do a lot of stuff about interpretability in AI and in healthcare as well. So I highly recommend you to watch the TED Talk as well if you want to. And the other thing about machine learning is AI biases, fairness. We heard a lot about it. So there's this specific course by MIT that's talk about AI biases and fairness. Really well documented video, highly recommend. And like how you guys say, we have like a lot of fairness, transparency, privacy issue that related to machine learning. And there's this book that's really good that I watched as well. It's called The Alignment Problem. It's by a professor in UCB. It's about how we can align machine learning with our humans' value. All of this stuff are linked. So if you have more, if you'd like to know more about like machine learning ethics and like how it actually can be dangerous, but I don't say I don't support it. I was like, machine learning is very helpful, but we need to be mindful that it can be perilous as well. So that's all from us, and we will take some questions. And yeah.
Okay, wonderful. So let's go to Doris. Is there a need for bigger capacity of laptop for machine learning? I'm using an old Mac.
This is actually a great question. This is like truly dependent on the data sets that you're working with. a lot of the times, at least in the universities, right, when they're dealing with huge amounts of data, they have to process this on the cluster, which is a cluster of server computers that will that are like way higher tech than anything you could purchase individually. But for the sake of implementing a small ML project, for the sake of learning about ML, or for the sake of like doing a fun small project, such as like attempting to write a image like recognitions like set with just a bunch of images, this is something that is very doable on most machines. Of course, it really depends on like, yeah, it will be software or like hardware dependent here, but I would say that like short of like being very, very old hardware, then you should be able to at least get the script working. But of course, if it doesn't, cloud computing is always an option. Google Colab is free, which is great. So it's honestly not any different from just accessing the IDE. And so like we really recommend that if you're interested in like things that will run really slowly, that you look into cloud computing on Google Colab.
Okay. Aviral, is it possible to use two types of different algorithms at the same time to increase the accuracy of the model?
It's not two possible model at the same time. I think it's normally like we actually use different model, and like different model has its own strength and weaknesses, I would say. So for example, like K and N, it might overfit very well, but then I think, for example, like the example that you have, right, like KNN versus logistic regression, it's not like we can integrate both two together. Like I think both KNN and logistic regression has its own like advantages and disadvantages. The idea is to test it against different kind of like ML model that's available out there, and to see like which ML model perform better on the current data set. So for example, like you can see that like KNN perform really well on the data set that you have just now, but then it doesn't mean that KNN will always perform better on like other data set that you are testing. So it's actually very recommended to use different data sets. But on the idea of integrating two machine learning models together to get higher accuracy, it might be possible, but I'm not really sure about that.
I would say like the close analogy is that if you can recall, well, actually, let's just go back to it. If you can recall the nodes that we have, right? You can think of each set of nodes as like a different transformation that you do to the data. So what is often the case is that your data will go through many, many layers, especially for things that are very complicated. And so this is not necessarily applying two different machine learning models, but like this kind of transformation is very iterative. And so this is like, we call them layers. So like you pass the data through one layer, and then you pass it through another layer iteratively until you get to this end output layer, right? So this actually goes into the specifics how the function works, but you will often have to make multiple layers to get good results from your data set, because this data is always complicated.
Mm-hmm. This is, and please excuse my pronunciation here. Effie writes, does ML help in cybersecurity?
Wait, the question is, does ML affect cybersecurity?
Well,
does ML help in cybersecurity?
So I think it does. So for example, I think I heard a lot of information about how like banks actually use ML to detect fraud transaction. So in terms of that kind of way, like there's a lot of way whereby ML actually help in try to prevent cybersecurity attack or like detect cybersecurity attack, especially like in a lot of companies, because it actually really well in trying to find pattern or like unusual pattern in a huge amount of data set. So I definitely think that it has a very huge application in cybersecurity itself.
Yeah, and if there's one takeaway that we want you to have from this, it's that the goal of what ML is really good at doing is taking a lot of data and finding connections between those data points. So anything you can think of that needs to process like a huge amount of data, you can almost always apply some form of ML if this data is meaningful, of course. So in terms of cybersecurity, like actually building firewalls and like those kinds of things, it doesn't have to necessarily do as much with processing huge amounts of data. But what, as Zad said, right, like with like fraudulent account accesses and things like that, that is something that is totally very like applicable to ML.
Okay. Madi asks, what is the AI application in video games nowadays? And as a machine learning developer, can I work in game field?
So yeah, so I can take this question. Yeah, so I don't know if you've seen, but I think the team OpenAI, I think, is run by Tesla or is like a subsidiary, or maybe
I think it's
Google.
Google.
It might be Google. Yeah. So OpenAI is a team that has been developing machine learning game software for quite a while, and a couple of years ago they like released like big news like Dota 2, which is one of the like popular MOBA games. They managed to write an AI that like beat a team of professionals. So this is like totally something that is doable in currently, and I recommend you check out the OpenAI, like the stuff that they've been doing. It's like really cool, and it's like definitely very marketable if you're interested in that kind of stuff.
I think in terms of game, like DeepMind also created an AlphaGo, which is like one of, I don't know whether that's considered as video game, but it's a game, which is like super huge at that time because it did like the world best Go player on planet Earth. It was like AlphaGo versus human. There's also a movie about it. It's called Go or AlphaGo, something like that. Yeah, highly recommended. Super.
Yes. So furthermore, like in terms of not just like video games, people are still developing things to just like test what we can use this for in terms of not just like these. So games are like have different classifications, and Carnegie Mellon actually solved poker a few years ago, which is like crazy because poker, you don't always have all the information. So there's so much more extrapolation that you need to do from a given subset of information. And so it's actually like very interesting how far that machine learning has come from being able to take such a small, comparatively small set of data and being able to generalize it to other things.
Okay, and Yashvi asked, just as you mentioned, we trained the computer for game 1,000 times. Was that the training part or the testing part from train test?
Yeah, great. So when we did reinforcement learning, the training over 1,000 times was simply to train the computer. When you're reinforcement learning, your testing part, you don't really have a test set, and as opposed to when you have like a big data set of images where you can like divide 80% of them to like train it and then like verify that your algorithm is or your regression is correct with the remainder 20%. In the case of the game, you just have like once you trained your AI, you just have your AI play the game. In which case, this is your testing phase. It's like, did the AI win? Like, in our case, it was like, how many points do the AI get on average? And so that is the testing phase, which doesn't actually use a data set, but rather just uses the game itself.
Okay. This is from Madi again. What is the AI application? Oh, no, I already asked that one. Sorry about that. Okay, from HW, besides Google TensorFlow, what other ML platform should we look into? Anything from IBM or Microsoft? I think you answered that one, right?
It's okay. So with the thing about libraries, like choosing the best library can be very hard, and this is like something that requires knowledge and like you to just jump into ML and see what works and see what doesn't. So what we recommend is that you don't concentrate so much on optimizing like right now everything. You want to get something that works with the knowledge and the skills that you have first before you can improve and try and optimize to get algorithms that are like very good for your data set and things like that. So
I think the other thing about like trying to find an ML library is to find whether it is well documented or like whether actually a lot of people have tried it as well. Like I personally doesn't know any library. Maybe I'm just shallow minded, but like I don't really know any library from like IBM and Microsoft, but I think they have a really strong IBM and Microsoft research team, and which I really admire as well. But in terms of TensorFlow, they are really, really well documented. There's a lot of example out there, a lot of Stack Overflow posts about that, which is actually very important when you actually face a bottleneck, right? Because you need someone to help you, someone to understand the data set. And everybody is using it. It was really well documented. So I would recommend TensorFlow if you are beginning, but like if you want to be more sophisticated, you can start to build your own neural network. I think that will be the most sophisticated thing that you can do.
And of course, we don't expect you guys
Yeah.
in CS50 to build your own right now, but in the future, just as consideration, there's a lot of statistical theory that goes into what machine learning is. And so there are Harvard classes or MIT classes that you can take that are just totally on like ML and applying ML. And if you are interested in talking about that, feel free to like reach out to one of us, and we'd be happy to chat with you.
Yeah. And so before we actually end, please take 1 minute to actually fill out this feedback form, which is tinyurl.com ML50 feedback. And we actually really thank you so much for actually coming. It's really late or like very early. I don't know what's the time zone, but thank you so much for actually coming. We actually enjoyed this very seminar, and we are very excited to share this. And we hope that you learned something too. So I think we can start.
So yeah, I think we'll be ending the recording now, but
Yep.
like stay a little bit after to answer any further questions.